guess I wanted to take you back to what we call the BC era, before calculator, and talk a little bit about how logarithms were used in the era before there were efficient computing machines. Now, just to remind you of a couple of things, we talked today about log base b, and in particular, the most popular logarithm used by scientists, engineers, was log base 10. And the reason for that is that log base 10 was very easy to compute for powers of 10. And since our number system uses powers of 10 all the time, it was a natural fit. So for example, the log base 10 of 10 to the third would be 3. The log base 10 of 0.01 would be the same as the log base 10 of 10 to the minus 2 or minus 2. And so you people who were working in the BC or before calculator era would develop some tricks. They would notice, for example, that if you took the log base 10 of a large number right here, then you could simply count zeros, because after all, 1 million is 10 to the 6th, and there's your logarithm. Ta-da! Same thing here, log base 10 of 0.0001. Rather than counting zeros, you count the number of times you had to move the decimal point over to get to 1. And that gives you -4. If that reminds you of scientific notation, it's because it's exactly like scientific notation. So, the only thing needed now, in order to get a full set of values for logs, would be some kind of pre-computed table of logarithms. And that's exactly what everybody had. I was able to find our table of logarithms on the internet. Ta-da! But this would usually be printed in the back of people's textbooks. And the way that you read this table, it's a little bit intimidating, but the way that you read this table is like this. These numbers that are in the box here are the logarithms, all the way down to the bottom. And it keeps going a little bit below, but I'm not going to take the screen that far down. And the numbers off to the side are the numbers that you're finding the log of, the first 2 digits, and then the third digit is the final digit of the number that you're finding the log of. So, for example, if I wanted the log base 10 of, let's see here, how about 3.00? Then I would consider 3.00 to have 1, 2, 3 digits, 3, 0, and 0. So I go down to the row that has 3, 0. And then, for my third digit, I would go to the column that has 0 right here, and right there, the table gives me the value of 0.4771. Notice there are some implied decimal points here, right? So it is implied that there's a decimal point between the first and second digits there, and it is also implied that all of these logarithms have a decimal point preceding them. You say, okay, well, what if I wanted the log of a number that was bigger than 9? How would I do that? Well, let's say I wanted the log base 10 of, how about 452, something like that. Then to get the log base 10 of 452, I would do a quick scientific notation rewrite. 452 is the same as 4.52 times 10 to the 2. And now, here's where our log properties become magic. The log of a product is the sum of logs. So if I can find the log of 4.52, then all I have to do is add to that the log of 10 to the 2, which is 2, and I'm good. So watch that carefully. Because, I wrote that wrong. Watch that carefully. Because 452 is the same as 4.52 times 10 to the 2, then I can take that scientific notation exponent and add it to the log of 4.52. Let's see here. On our chart, we go to 45, and we go to the column whose digit is 2, and that puts us right here, 0.6551. And we add 2 to it to get our final number, 2.6551. So that's how logarithms were found. This table had two purposes. You could also use it as a reverse lookup table. Suppose that I knew that log base 10 of x was equal to 3.15, and I wanted to find out what is x. Well, I can write x as 10 to the 3.15, but that doesn't give me a whole lot of insight. But the log table could be used to find the value by breaking up the 3.15 into the decimal part and the integer part. The decimal part, by the way, was called a mantissa. And the integer part was called the exponent. So I can think of this as 3.15 is 3 plus 0.15. This part I'll look up, and this part will become my scientific notation exponent. When I go and look up on the table, the reverse lookup happens like this. I scan along for the number or numbers that are closest to 0.150. I've got 0.1492 here and 0.1523 there. 0.1492 is the closest, and so into the 3.15 is going to be equal to 1.41 times 10 to the third, or 1410. So that's how this table was used. It was used to look up logs, and it was used to reverse that process for compute powers of 10. Now, let's see how this log table made our computations magically much easier. I want to consider a couple of computations here. Let's first of all consider multiplying 6,110 by 452. Now you learned how to do this back in grade school, and you remember that it was a pain in the neck. You had to multiply the 2 times everything, shift over one place, multiply the 5 times everything, shift over another place, multiply the 4 times everything, add it all up, hope you didn't make a mistake, so on and so forth. That process would take, if you got good at it, that process would take you a good 3 minutes or so. The log table made these multiplications actually fairly simple, and here's why. If I take the log of the product, 6110 times 452, then according to my log properties, that should be equal to the log of 6110 plus the log of 452. In other words, by using a logarithm, I can turn a multiplication problem into an addition problem. And so the plan became that you would take each one of your factors here, and you would find the log of that factor, and you would add up the logs of the factors to get the log of your answer. And then you could do a reverse lookup to find out what your answer actually was. So let's actually do that. First, think in terms of scientific notation. This guy is going to be 6.11 times 10 to the third. This guy is going to be 4.52 times 10 to the second. And so if I now go to my table, and I'm going to look up 6.11 times 10 to the third here. Here it is in my table. I go down to 6.1 right here, and 1. And that value is 0.7680, excuse me, 0.7860, 0.7860. So the log of 6110 is going to be 3.7860. Notice that I'm adding the scientific notation exponent here. And likewise, 452 is 4.52 times 10 to the 2. So I go back to my log table and I find 4, 5, and the column is 2, so that I have 0.6551 plus 2. And in just a matter of a few seconds, I have managed to look up the logs of both of my factors. And now we add 1, 1 carry the 1, 4 carry the 1, 4 carry the 1, 6.4411 is the log of the product of these two numbers right here. Let's go back and do a reverse lookup, remembering that we're going to split exponent and mantissa. I'm going to look up 0.4411, and then my final answer will be times 10 to the 6th. Let's see here on the table, 0.4411 looks like it is right closest to 4409. 4409 is 276. 2.76 times 10 to the 6th is the product of these two numbers. Now, that's limited to 3 significant digits. And back in the day, we learned tricks to squeeze one more significant digit out of it by a process called linear interpolation. But this is sufficient for a fair amount of scientific and engineering work. Let's actually check this just to see if we did it right. If I pull up my handy-dandy calculator, forgetting for a moment that we're living in the BC era, then according to my calculator, the product of 6110 and 452 is 2761720. And you can see that to 3 significant digits, we nailed it. And that's really all that's needed from an engineering perspective. Well, the logs had more tricks up their sleeve. We could also use logarithms to do division. Division was a real pain in the neck in elementary school, if you remember. If you wanted to divide something like 21 divided by 452, then you had to set it up in the long division format, and you had to add some zeros and do some guessing and multiplying and subtracting and blah, blah, blah. Not very pleasant. But with logarithms, we can remember that the log of a quotient is the same as the difference of logs. And so to evaluate this quotient right here, all I need to do is to compute the logs of each one of my numerator and denominator and subtract. And that will give me the log of my answer. And then a reverse lookup will give me the final quotient. And that's not so bad. Let's do that. See if you can beat me to it. Here's the log table. Pause the video and see if you can do 21 over 452 using just the log table. Welcome back. I get the log of 21 is going to be equal to 1 plus the log of 2.1, which is 0.3222. And the log of 452, we already figured out. 452 was right here. 452 is going to be equal to 2 plus 0.6551. Okay, well that gives me my two values. Oh, lost them. 1.3222 and 2.6551. 551. And now we do some subtraction. Now the subtraction is a little bit ugly because I'm subtracting a larger number from a smaller number. So that did require that we reverse that and give it a negative sign. So when we subtract, we got 9. We had to borrow 1. So that actually gives us 2 right here. And 3, and 3, and 1. So our final, the log of our answer was 1.33, excuse me, negative 1.3329. Now the negative sign was a problem for us log table users because if you think about it, this is negative 1 minus 0.3329, and my log table does not have any negative values in it. And so you might think that all we had to do is just reverse the sign and everything was cool, but actually that doesn't make a whole lot of sense if you think about how the log properties work. So instead, we resorted to a trick back in the day, and the trick that we would use was to add 1 and subtract 1. We would get rid of our negative value right here by adding 1 and subtracting 1, so that we rewrote that as negative 2 plus. And now when you add 1, that's going to give you, well, we call it 1's complement of this thing, which is going to be 176, just like that. Take a moment to check for yourself that when you add negative 2.6671, it's the same as negative 1.3329. Now, how did that help us? Well, we do a reverse lookup on 0.6671. And I go to the table and I find 0.6671, not quite there. 0.6628, 0.6665, 0.6670, there it is. And that gives us 4.65. And then here's our exponent, times 10 to the minus 2. And you can imagine that with just a little bit of practice, this was a lot faster than doing long division of 452 into 21. Well, the final bit of magic with logarithms was computing powers. Imagine for a moment computing 3.81 to the 5th power. Now you could do that by hand, but you would end up multiplying 3.81 times 3.81, and then taking that product and multiplying it by 3.81 again, or if you were really clever, you might square that product and then multiply by 3.81. Anyway, you'd be doing a lot of computations. But logs turn this into a fairly simple computation because the log of 3.81 to the 5th is the same as 5 times the log of 3.81. And so our plan would be to look up 3.81, find the log of that, multiply the log by 5, and that would be the log of our answer. And so back to the table, we find 3.81. Let's see, here it is, 38, and the column is 1. So we have 0.5809. And multiplying by 5 is not a terrible hardship. We can certainly do that. That's going to give me 5 carry to 4. That's going to give me 0 carry to 4. 9 carry to 2. And there is the log of my answer. So that my answer is going to be something times 10 to the 2. And if I go back to the log table and find 0.9045, looks like it's going to be between 9042 and 9047. That's going to be 80, this is the closest digit, 8.03. Times 10 to the 2, or 803. That's not bad, especially considering that the alternative was to do 4 different multiplications. If we actually pull out the calculator and compute it, the calculator gives us 802.832377. Which, to 3 significant digits, is exactly what we were looking for. Well, I wanted to do all this to give you a flavor of why was it that logarithms were invented, and why did people place so much interest in them? Why would John Napier spend 30 years compiling a log table? I think you can see that his work was really an investment into simplifying calculations for everybody. When the calculator came along, then the calculator superseded it, but in the internals, the calculator is still going to use logarithmic arithmetic for computing exponents. One more point, and that's kind of interesting, and that is that the calculations that we did numerically here also form the basis for the logarithmic differentiation that I talk about in the other video. I hope that